This will be looking at the fields of view of binoculars and telescopes. One of the units that we'll study in this class is learning about telescopes of different types, and binoculars are just pairs of telescopes put together. This is a picture I took down in Oregon one time, and this is a fairly wide field of view. And you might see a view like this looking down a large short pipe or something like that. If you look down either a longer pipe that's the same diameter or maybe a shorter, smaller diameter pipe, the field of view might shrink. If instead you look down a paper towel tube or an even longer, large pipe, then the field of view might shrink even more. And most of your field of view in this case, the field of view that you care about is the picture that you're seeing there, but your field of view might also encompass a bunch of the inside of the pipe, which is pretty much worthless. So just what is a field of view? It's what you can see through some kind of an observing instrument. And the instrument could be a telescope or binoculars or your eye or a window or something like that. Usually we talk about it being the angular width of what you're able to see. And we're going to measure this in degrees today, fractions of degrees at times, decimal fractions of degrees, but we'll say the field of view is so many degrees or something like that. Here's another example of a field of view. And this is going to show another way that the field of view might shrink. You might have some combination of lenses that might magnify an image. If you look at an unmagnified image, you're just looking down whatever tube it is that you happen to be using. But if you start putting lenses in there with a small magnification, the field of view shrinks slightly. With a larger magnification, the field of view, the part of the world that you see, shrinks a bit more. And as you bump up the magnification with this same instrument, the field of view that you see through that instrument continues to shrink, getting smaller and smaller. Looking at this, you can see how the image degrades as we increase the magnification and shrink the field of view. Sometimes this is caused by bad optics, and sometimes it's caused by looking through the Earth's atmosphere. If you're looking at something close to the horizon and you try to magnify it, you may just see pea soup like this. Sometimes the effect is caused by the wave nature of light, and in that case, magnifying the image will do no good whatsoever. And so there's a limit to how much you can shrink the field of view and magnify things. Even if you were looking through a perfect vacuum with very good optics, the wave nature of light would eventually take over. We're going to be using a numbered scale outside, and I made the dimensions on this such that if you were a particular distance away, then the distance between these things will be well calibrated. And if we have a 26.2 meter distance from this numbered scale to our telescopes and binoculars, then the distance from 4.5 to 5.0 on the scale, it actually goes from 0 to 10, but if you're just seeing this part of it, that would be a 5-degree field of view. And so going from the left side of this bold line here to the left side of this bold line is exactly half of a degree. The distance from one of these to the next one of these lines is 0.1 degrees. It's just the left side of those heavy lines that matches up with these finer lines down below. So I try to use the left side of them when I'm doing things, and that will help out a little bit. The finer divisions on here, one of those fine lines to the next one is 0.01 degrees, a hundredth of a degree. And so we'll be able to shrink fields of view down to where all we're seeing is those fine lines sometimes. Now, if your eye is at the right distance from the lens or eyepiece, you'll be able to see the full field of view. If you're not, if you're backed off a ways, you may not see the full field of view. And it's tricky to get that just right. When we actually do this outside, what I have people do is get their eye as close to the lens as is comfortable, and if you move as far to the right as you can, you'll see the maximum amount of the left side field of view, and if you move as far to the left as you can, you'll see the maximum of the right side field of view. And so I encourage people to move their head back and forth just a little bit when they're looking through the telescope. Now, how large is this field of view? And let's see if we can measure it to the nearest hundredth of a degree, and go ahead and give it a shot here on your own. You could pause the playback, and then I'm going to count it out here and see what we get. Okay, here's what I will do. I'd start over here at this mark on the left end. Sometimes I have you take the right edge reading and subtract the left edge reading, and I'll do that here, but first I'll just say on this heavy bold mark right here, we're just about seeing the left end of it. And so each one of the heavy lines, the left side of each of the heavy lines will be another tenth of a degree, 0.1 degrees. So this would be 0.1, 0.2, 0.3, 0.4, 0.5, and now I'm going to count the fine divisions. So this left side of this bold line would be 0.50. This next line will give me 0.51, 0.52, 0.53, 0.54, and I'm almost to 0.55. So I'd estimate this field of view is either 0.55 degrees or maybe 0.54, but probably pretty close to 0.55. So when we're getting down to the nearest hundredth of a degree, we're really splitting hairs, and I don't worry about missing by 1/100th of a degree on this. Now we've changed the field of view, and we can do that by swapping out in a different eyepiece. People don't realize that using different eyepieces on a telescope changes the magnification. And a common question when we have a public stargazing event, someone will come up and say, "What's the power of your telescope?" And I know what they mean. They mean, what's the magnification? Because that's the way most telescopes are sold. Unfortunately, it's actually not that important. But I'll have to do a calculation in my head that we'll learn about when we study telescopes in a week or so. Whoops, let's go back to this one and figure out the field of view that we have here. Now, this time I don't see a nicely placed heavy black line over there. However, I can see for sure 2/10 of a degree. Going from here to here is 1/10 of a degree. From here to here is another 1/10 of a degree. So that's 0.2 degrees. And then I'm going to count how many lines I see to the left of this one and how many I see to the right of the left edge of this one. And again, I'm using the left edges of these things. So this would be 0.01, 2, 3, 4, 5, 6, just about 7. That's about 0.07 degrees. And then starting here, 1, 2, 3, about 0.03 degrees, and 0.03 plus 0.07 that I had over here is 0.1. And so I've already got, this is 0.1, this is 0.2. I'd say the field of view here is about 0.3 degrees. And so kind of hard to figure that out, but see if you can wrestle with these things. Remember, the distance from the left edge of one bold line to the left edge of the next is 0.1 degrees, and the difference between two adjacent fine lines is 0.01 degrees. Here's even more magnification on our image. How much do we see here? In a case like this, it's almost easiest to just count the hundredths, although if you go from the left edge of this bold line that you can just barely see here, okay, count that as your 0. Going to the left edge of this one is 0.1 degrees, and then 0.11, 0.12, 0.13, 0.14, and about 0.15 degrees. So 15 hundredths of a degree is what our field of view happens to be here. This is a picture of where we actually set this up when we do it outdoors. And you can see it goes from 0 on the left end over to 10.0 on the right end. It's in 4 pieces. That's just the size of the lumber that I happen to be using. And I actually put the paper on MDF is what it's called, medium density fiberboard, and kind of glued it on there. But that's the scale, and you can't even see the fine divisions on it from here. But I just take it out and lean it against the back wall of the building. This is what the field of view might be looking through something, maybe a pair of binoculars. Oh, I wanted to talk about how some of the readings, like for the binoculars and the finder scopes, I have you record the right end reading and the left end reading. And if I look at the right end on this thing, here's 8.0, 8.5, 8.6, 7, 8, 8.9, and this is just about 0.90, is just barely showing here, or 9.0, excuse me. So that would be the right edge reading, 9.0, and then over here on the left, I've got 2.5 right here. Going to the left, this would be 2.4, and so the field of view here would be 9.0 minus 2.4, whatever that happens to be. Let's see, 9 down to 3 is 6.6 degrees, something like that. And you could also get that if this is 9.0, 8, 7, 6, 5, 4, 3. Okay, 9 down to 6 is 6 degrees, 6.5 degrees, 6.6 degrees. So different ways of getting the same determination, but sometimes I do have you record the right end and the left end and subtract to get those things. Now this is blown up enough so you can actually see the hundredths mark on there, although if I was looking at this, I don't think I'd bother to try to figure out the hundredths. Usually 2 significant figures is good enough, and so here I'm going from 5 down to 2. That'd be 3.0 degrees, and then 3.123. So this is about 3.3 degrees. And see if you can come up with numbers and agree with me on that. Okay, this isn't a very good picture. I took it with my cell phone, and it's looking into the I don't know which eyepiece I happen to be using on here, but it's looking into the telescope eyepiece, and your eye can do a better job of seeing these things than my cell phone can. I had high hopes that I'd be able to get nice sharp pictures using my cell phone, and it just didn't work out. But that's kind of what it looks like when you're looking through the thing. And by the way, the scale gets turned upside down when you're looking at it through the telescope. So the hundredths will be on top, and these fine divisions up here are the hundredths, and then the bold ones are the tenths of a degree. For one of the telescopes, this is the Eyepiece Case, and got various things in here. This is actually the finder scope up here, and then here's a different kind of finder scope that we use when we're out under a dark sky. It would be completely useless in the daytime, because what it has is an illuminated bullseye on the thing, and you just can't see that in the daylight. And then I've got eyepieces of various focal lengths in here, and that's what changes the magnification. And then I've got stuff like, I think this one has spare batteries and things like that, that there's kind of a necessity for when you're out there. I'm going to switch over here. Let's see. Putting our knowledge to use, we're going to be using a star atlas in here. And star atlases, I'll show you a picture of one here in a minute, but this is a page out of a star atlas. I can't remember which one this happens to be. If you happen to get into astronomy as a hobby, you may be using a star atlas, either a printed one or one that's on a computer. So here's something. Altair is a bright, easy to find star. And down here is the wild duck cluster, which is not so easy to find, but it's something that you can track down through a telescope. And you'd like to find your way from Altair to the wild duck cluster. Okay, now suppose you have an eyepiece that has a 0.3 degree field of view. So that's your eyepiece. And you find something easy like Altair in it, and then you work your way down to the wild duck cluster, which is going to be a whole bunch of fields of view. And in this star atlas that we're looking at here, many of those fields of view coming down here aren't going to have anything in them, because this star atlas just doesn't have that much stuff in it. And what you would do is, if you were doing this kind of star hopping, you'd find something you can find, like Altair, nice bright naked eye object, and then you kind of nudge the scope over. Sometimes you can do it by turning dials on the mount of the telescope. Sometimes you just kind of nudge the telescope to change the field of view a little bit, and then you change the field of view again. And it's hard to do it along a straight line. You want to be looking at a star atlas continually while you're doing something like this. Look through the eyepiece, look at the star chart, go back and forth, back and forth. It would be impossible with a 0.3 degree field of view to hop from Altair down there to the wild duck cluster. So what else can you do? Here's what you might do with a finder scope. A 5 degree field of view, a finder scope might have something about that big. They vary depending on the manufacturer and the particular optical characteristics. But with that, here's what you would do. You'd get Altair in the field of view, and then you'd look at the adjacent field of view, sliding it over until you see this star field in your field of view. And then you slide it over a little bit more until you see this one in your field of view. A little bit more, and you get to the wild duck cluster with about 5 field of view hops. But the nice thing is, every one of these fields of view has some recognizable pattern of stars in it. So when you get your finder scope centered on that, you know that that's your correct field of view at that time. You may have to mentally turn it upside down, because your finder scope will produce upside down fields of view. Or an easier thing to do is take your star atlas and turn it upside down, so that it's got the same view that you'll be seeing through your finder scope. By the way, one thing you have to make sure that you have is that your finder scope is aligned correctly with your telescope. And the finder scope actually has a pair of crosshairs in it. I didn't make a note of this, but actually let me pop back to something here. And in this thing, the eyepiece box, one of the eyepieces that I have in here, and it's, try to change the view or get my laser pointer back here. This eyepiece right here has a pair of crosshairs in it, and then this little thing right here is a light that screws into the side of the eyepiece and illuminates those crosshairs. It's adjustable brightness, and our usual classroom observing site, I'll aim the telescope at Beasley Hill on the west side of Ephrata. There's a radio or an antenna of some sort on the hill up there, and I'll get the top of that antenna, which has a blinking red light, right on the crosshairs of the telescope. And then I'll track it down through the finder scope, and the finder scope I can adjust the aim of it without changing what the telescope is aimed at by turning a few thumb screws. And I'll turn those thumb screws until, looking through the finder scope, I've got the crosshairs directly on that same light on top of the antenna. And then my finder scope is aligned with the telescope. And then anything that is in the crosshairs of the finder scope will be in the crosshairs of the telescope. So that's a little bit of a process that I have to go through. Okay, gonna skip ahead here. There's some activity, we already did that. Here's the data that I gathered last fall when we did this as an online thing for the first time. And this is going to be in your lab packet, so you'll be able to see what these things happen to be. And unfortunately, you don't get to go through the experience of setting this up. Sometimes I go from one eyepiece to the next, and I actually have the field of view stay just about the same, like with this 40mm eyepiece and 32mm eyepiece. If I had all the same type of eyepiece in general, as I go from a large focal length, 40mm is considered large, to smaller ones, the field of view will continually shrink. However, my eyepieces are made by different manufacturers. They're different designs of eyepieces, and so while the tendency is mostly there, it's not always matched up perfectly. So it doesn't work out perfectly. But let me show you something that you'll do as part of this lab. One of the star atlases, and I think it's the one that I took your diagram out of. This is Uranometria or Uranometria 2000.0. This is volume 1. There's actually 3 volumes to it, but I just bought, actually living where I do, I could probably just about get by with this one alone, except sometimes I look a little farther south than -6 degrees. So I do have volume 2. And the part that we're going to be using today is, I think it's page 117 for this lab. It's got Vega up here. Most of the time it doesn't identify the stars by name, but I think if they're above a particular magnitude it does. So Vega does get a name on it. Other stars in here might have names, but I'm going to have you figure out how many star hops it would take to get, or fields of view, to get from Vega down here to the Ring Nebula. And I'll have you make circles on a transparency that are the correct diameter for the finder scope and for the one of the eyepieces, the 9mm, I think. But let me show you the process for doing that. I went and blew up this part of the diagram as much as I could, and this is showing the extreme upper left-hand corner of the page that we've got in there. And something you can see is coming down the left, the vertical margin of it is a scale in degrees. And so we can use that to figure out the size circle that we would need for finding these things. Don't use the horizontal scale that goes along here. This happens to be right ascension, and so this is 19 hours, 0 minutes, 18 hours, 56 minutes, and so forth. We're not going to be using that, so just use the vertical scale. Now, suppose that we had an eyepiece that had a field of view of 0.55 degrees. Okay, here's how I would make a circle that would fit that thing. By the way, I made my transparency out of a Ziploc quart-size bag. You could probably get away with a sandwich bag if you wanted to. Maybe. I'm not positive about that. But I would... Now, you won't be using a blown-up version of it like this. You'd actually want to use this version. But if it's 0.55 degrees, that would be the distance. There's 39 degrees. Here's 38 degrees. Halfway between there would be 0.5 degrees. And I would just go a smidgen past that halfway between there. Now, I don't want to use it on this one because this isn't the right scale that I have over here. But if I wanted a 0.55 degree thing on this one, I'd try to put it in the middle of my transparency. Okay, this is probably about 0.55 degrees, so I would just draw a circle with that diameter. All right, now that's not a perfect circle, but it's good enough for what we're doing here. And then suppose our finder scope happened to have a, I don't know, maybe a 6-degree field of view. Okay, how would I get that on here? Well, it's the distance from, let's see, 30 up to 36. And so 30 to 36 is up there. I'm going to want a circle that's like that. Now, I'm not that good at drawing circles, and so what I might do is take my, well, as you can see, I'm not that good at drawing circles. Take this thing, and I get 9.5 centimeters for the length of that line. If I cut it in half, that would be about 4.8 or so. And so there's about the midpoint of that thing. And if I take the midpoint and put it at 33 and then go up to 36 and down to 0, there, I might be able to draw a circle of that with those being the extremes. And so if you could draw a nice circle without having to mess with that, more power to you, but I'm just doing it this way. And so there I go. And then how many star hops with this thing would it take to get from Vega down there to the Ring Nebula? Well, no matter what I do, I can't quite do it with one field of view with this 6-degree field of view that I made up. And so I'd have to go to a second field of view, but not very far into the second one. In fact, if I had Vega in there, and I had some of these other things showing up in there, and I was looking through the finder scope like at this, I know that it's going to be just beyond this side of the field of view here, you know, so maybe I look for this line of stars here or something like that. And then I slide it over a bit and I start picking up this star, which is going to look fairly bright in the finder scope. The size of the dots signifies the brightness of the star. And then I just go a bit farther and I get that. And so I might do something like that. One of the questions I ask in there is how much bigger is the circle for the finder scope than the circle for the eyepiece? And here's how I figure that out. I say the mathematical operation that's the inverse of multiplication may help with this. Well, the inverse of multiplication is division. Here's what I do. I measure the distance from here to here, and I get that 95 or 9.5 centimeters. And then I measure the size of this one, and this is about 8 or 0.8 centimeters. Okay, so then I would just go, all right, well, let's see. 9.5 divided by 8, that's going to be about 12. Okay, and so I would say then my finder scope diameter is 12 times bigger than the eyepiece diameter happens to be. And so that's what I do. And again, you don't have to spend a lot of money to get a transparency for this lab. In fact, if you want to practice, you could practice on this part that says Ziploc on it and save this one for your more formal efforts. So, All right, that is what you need to know for the Field of View lab.